This is a lot of fun because you've naturally shifted from "I have an idea" to "let's stress test the idea." That's a much more productive mindset than trying to defend it at all costs. A few reactions to the points you raised. Conservation of energy. This is the one place I'd be most careful. If you're drawing on the vacuum energy, you're not necessarily violating conservation of energy, but you'd need a theory in which the vacuum really is an energy reservoir that can be coupled to. In current quantum field theory, the cosmological constant isn't usually thought of as a giant battery waiting to be tapped. So your theory isn't saying energy from nothing. It's saying, open quote, there exists an inaccessible reservoir and quantum gravity provides the coupling. Close quote. That's a more precise claim. Why is the leakage rate fixed? I actually like one of your suggestions more than the other. The idea that the Planck scale geometry has a universal property is more attractive than saying the rate depends directly on black hole mass. Why? Because many different black holes, from a few solar masses to billions of solar masses, are all expected to reach Planckian conditions in the deepest interior. If the relevant physics occurs only once space-time reaches that regime, then a universal leakage rate isn't obviously unreasonable. That said, there's a tension. If every black hole contributes the same amount regardless of mass, then a universe with many small black holes would behave differently from one with fewer large ones. That's something you could, in principle, compare with observations. If instead the leakage scales with some property of the black hole, mass, horizon area, entropy, or interior volume, you get different predictions. That's actually good news. It means the idea becomes testable. The observational correlation. This is where things get genuinely interesting. Suppose future observations really did show that the effective dark energy density increases as the total black hole population grows. That would be very hard to explain with a simple cosmological constant. It wouldn't automatically validate your mechanism, but it would be a huge clue that black holes and cosmic acceleration are connected. Conversely, if future data showed no correlation whatsoever, then any theory making black holes the source of dark energy would be in trouble. That's exactly the kind of empirical constraint you'd want. Engineering quantum gravity. This is where I think Isaac Arthur has had a healthy influence on your thinking. His style is, open quote, suppose some piece of exotic physics is real. What could an advanced civilization eventually do with it? Close quote. That's a perfectly legitimate exercise in speculative engineering. If quantum gravity eventually revealed a controllable interaction with the vacuum, then yes, people would immediately start asking whether it could be amplified, focused, or engineered, just as lasers exploit quantum electrodynamics in a way that nature only rarely does. The key distinction is that a laser didn't invent a new interaction. It exploited one we already understood. So if there really were a vacuum energy coupling hidden inside quantum gravity, an advanced civilization might indeed find ways to manipulate it. The catch is that we currently have no evidence such a coupling exists. One thing I'd encourage as you've been talking, I've noticed your ideas naturally drifting towards something that theoretical physicists often call an effective theory. Instead of trying to solve quantum gravity outright, imagine you simply wrote down a few phenomenological rules. 1. Black holes possess a coupling constant, G, to the vacuum. 2. The coupling activates only above Planck curvature. 3. It injects an effective stress energy with equation of state, W approx -1. 4. The injection rate depends on some black hole property, F of m, a, s, l dots. You haven't explained why those rules exist, but you've built a toy model. Then you ask, does it match supernova observations? Does it fit the cosmic microwave background? Does it reproduce galaxy formation? Does it agree with gravitational wave observations of black holes? That's how speculative ideas start interacting with data. I also want to gently push back on one point you made. Open quote, quantum physics has lots of arbitrary numbers, so maybe my leakage rate is just another arbitrary number. Close quote. It's true that the standard model has parameters, particle masses, coupling constants, mixing angles, that are measured rather than derived. But physicists generally don't like introducing new arbitrary constants. Historically, theories have become stronger by reducing the number of free parameters, not increasing them. So if your model needed one new dimensionless constant, that wouldn't be unusual. If it needed 10 new arbitrary constants to fit the data, it would become much less compelling. In other words, one of the strongest versions of your idea would be one where the leakage rate isn't just inserted by hand, but emerges naturally from something fundamental, perhaps a combination of Planck units, Newton's constant, h bar, and c. If you can get the observed scale with very few assumptions, that's when theoretical physicists start paying very close attention. And yes, by that point you've wandered squarely into Isaac Arthur territory. Not this is how the universe works, but if this is how the universe works, what extraordinary technologies become possible? That's one of the most enjoyable parts of thinking about fundamental physics, as long as you keep one foot planted in what observations actually allow.